So in order for a chemical reaction to actually happen, several things actually have to occur in order for a chemical reaction to actually take place. The big picture idea of this is understanding the concept of collision theory. That is, there's a set of statements that give the necessary conditions in order for a chemical reaction to occur. And the reality is we need three things in order to take place. The first thing we need is molecular collisions. In order to convert reactant to product, molecules have to collide. It's a pretty straightforward concept. Without those collisions, we simply would not be able to convert reactant to product. The next is activation energy. The molecules have to have the ability, or have enough energy rather, in the collision that they have in order to break the bonds, in order to convert between reactant and product. And then lastly, the collisions themselves have to have proper orientation. That is, they have to collide a certain way in order to be able to go from reactant to product. So as you can see in the example down here below, concentration is one of the factors that plays a role in regards to the rate of a chemical reaction. When you have a low concentration of molecules, you get very few collisions, and thus, very few of those molecules will be converted between reactant and product. However, the higher the concentration, the more collisions you end up having. More collisions means it's more likely that we are going to convert reactant into product, and as such, we end up having a higher rate of reaction. So let's talk a little bit about molecular collisions themselves. It's pretty obvious that two reactants have to collide in order to make or break bonds. Pretty straightforward. Without that collision, we simply cannot convert reactant into product. Most often, reactions in the liquid or aqueous and gas phases tend to happen more often because it's more likely that the molecules are going to come in contact with each other. This has to do for a couple of different factors. First off, the surface area of those molecules. Those molecules tend to be spread out very far apart, and so the surface area of liquids, aqueous solutions, and gases tends to be much larger than that of a solid. If you take a look at the solid example on the right-hand side here, you'll notice that only the molecules that are on the surface are going to be able to react with any material it comes in contact with. However, the liquid being something that has more ability to move, more of those molecules can come in contact with other materials, thus resulting from reactant into product. This is something we end up seeing in lab, where we notice that the ionic substances that are dissociated into water, because they're free moving, are much more likely to react than, say, covalent substances, which tend to be bonded together and require more energy in order to react them. So part of the molecular collision aspect just simply has to do with the state of matter that they are in. Solids tend to react very slowly, whereas liquids, aqueous solutions, and gases tend to react at a much faster rate. Another factor that plays a role in this is activation energy. This is the minimum amount of kinetic energy that the reactant particles must have in order for a collision to result in a reaction. Slower reactions tend to require more activation energy. That is, reactions that are slower just simply need more energy in order to overcome the activation energy to go from reactant into product. Faster reactions do require less activation energy and thus result in a much faster reaction because they don't require nearly as much energy to convert between reactant and product. An example of a chemical reaction that is very slow, that requires a lot of activation energy, is rusting. When water comes in contact with iron, it will naturally rust. However, because the iron has a high, or the iron and the water need a high activation energy in order to convert to rust, the reaction happens very, very slowly. And some reactions happen very fast. You see quite a bit of these in lab when we react two chemicals together and they instantaneously get converted between reactant and product. Well, that's because they don't require a lot of activation energy in order for that chemical reaction to take place. Another factor plays a role here is collision orientation, and that has to do with the fact that the molecules need to collide with each other in a certain way in order to make the desired product. So if I take a look at the example on the right-hand side here, we're trying to make carbon dioxide, and in order to get a proper orientation, the carbon dioxide, or the carbon monoxide that is here, has to collide with the NO2 in the proper way in order to produce not only the correct atoms of CO2 that's here, but also the correct structure. Notice that in CO2, the oxygen that is on the CO molecule here has to bond with the carbon. So in order for a proper collision to take place, the carbon of CO has to collide with the O of NO2 in order to produce the correct molecule. Notice here we have no reactions for these three because here, even though oxygen is colliding with the CO molecule, it's not in the proper orientation. The carbon would have to collide with this oxygen in order to produce an effective collision to produce a CO2 molecule. In addition to that, the oxygen of CO colliding with the nitrogen, or even the carbon colliding with the nitrogen, does not produce a correct collision because of the improper orientation. In order to produce a proper orientation, the CO has to collide with the oxygen in order to create the appropriate CO2 molecule. So undesired orientations do not result in a conversion between reactant and product. Now this is something that we do not necessarily have control over. We can't control exactly how these molecules will collide. We can just change factors as in the amount of energy that's present in the molecules, the number of effective collisions, and those types of things. And then again, as previously discussed, the nature of reactants down below, ionic substances react much faster than covalent and molecular compounds because when ionic substances are dissolved in water or dissociated into aqueous ions, they're free-moving. And free-moving ions will react much easier than those that are stuck within chemical bonds. Because the ions are free-moving, there requires significantly less energy to be able to convert between reactant and product. So as a result of that, we end up with a collision that is more likely to convert between reactant and product. All right, so the next thing we're going to analyze tonight is we are going to take a look at reaction rate. And reaction rate is just simply the rate at which reactants are consumed and products are produced in a reaction in a given time period. So very similar to how we can agitate a chemical reaction, or we can agitate a solution in order to make more or speed up the process of the dissolution of the reaction. We can use some concepts in order to make the chemical reaction happen faster. And these are things that we are going to explore in lab when we get to our lab over the nature of chemical reactions. But if you take a look here, this chemical reaction is the process of rusting. Rusting is not a very fast process, which is indicative of it having a very high activation energy. It requires a lot of energy in order to be able to convert between iron, water, and iron oxide, which is the chemical formula for rust. So the first thing I want to look at is physical states of the reactants. The first thing we want to take a look at is surface area. Generally, smaller particles will react faster, and this has to do with the greater surface area. Very similar to when we dissolve a substance, greater surface area, things like crushed ice versus cubed ice. The crushed ice has a greater surface area, so therefore is going to melt faster, resulting in a faster rate of dissolving. Well, it's the same with chemical reactions. If I have a chunk of magnesium versus some powdered magnesium, the powdered magnesium will react faster because it has a higher surface area when compared to that of the chunked magnesium. So if I look at the diagram here on the right, the only molecules that have the ability to react with the molecules that are in the solution that are surrounding it are the ones that are on the outside. Reason being is that they're the only ones that have the ability to come into contact with any of the molecules to be able to convert between reactant and product. If we break up the magnesium, like what we've done here, well, the magnesium now has a greater surface area. And because it has a greater surface area, more of the molecules have the ability to collide with one another in order to be able to convert between reactant and product. So one thing I want you to consider is the physical state of the reactants and products in order to be able to convert between reactant and product and determine the rate of the reaction. If I look down here at the bottom, this down here is going to have a much faster rate of reaction in figure 2 than will be in figure 1 because the surface area of the molecules in figure 2 is greater, which results in more frequent collisions, resulting in a conversion between reactant and product more frequently. So make sure when you're answering those questions that you correlate the concept with the ability to have effective collisions with one another. That's the whole goal here. Remember, it's all about collision theory. And when we're describing changes we're making in chemical reactions, we need to make sure that we tie it back to the fact that we have more effective collisions in figure 2 than figure 1 due to the fact that we have a greater surface area, more collisions, greater opportunity to convert between reactant and product. Next is the concentration. Simply put, a larger concentration results in more frequent collisions and thus the faster rate of reaction. Again, make sure we correlate that to collision theory. So if I take a look in the very first example here, this very first example has very few molecules that have the ability to collide with one another. They'll still convert between reactant and product, but the process in which we are converting reactant and product is very low. On the right-hand side here, because we have higher concentrations, we have more molecules that have the ability to collide with one another, resulting in a greater opportunity to convert between reactant and product. So if we can see on the right-hand side here, we have a greater concentration. Greater concentration results in more collisions, thus the rate of the reaction is greater. Again, remember, we're tying all of this back to the rate at which a chemical reaction takes place and how that's correlated to how many collisions or effective collisions molecules have with one another. The next is reaction temperature. Temperature is simply a measure of the kinetic energy of the molecules that are present in the solution. The more speed causes more effective collisions. This allows more molecules to be able to overcome the amount of activation energy that is needed in order to be able to start the chemical reaction. The rate itself doubles roughly every 10 degrees for an increase in temperature. So if we're going from 20 to 30 degrees, we should see a double of an increase in temperature. 20 to 40 degrees, we would see a 100-fold increase in temperature. I want you to consider human body temperature and how important it is for us to be able to maintain homeostasis. That is, the ability to maintain and regulate a stable internal environment. Simple changes in temperature, whether it be 10 degrees above or 10 degrees below normal body temperature, would either double or halve the ability for the chemical reactions to take place inside of our body. So temperature plays a very important role in humans and their ability to live, because they have to be able to convert between reactant and product efficiently. We don't want to get our body's temperature too high, otherwise our cells won't be able to function, but too low, we can't convert enough reactant to product and perform the chemical processes necessary in order for cells to be able to survive. So remember, the temperature is a measure of kinetic energy. More energy in those collisions, they're more likely to overcome the activation energy and result in a more effective collision. Last one is a catalyst. And catalyst is a substance that increases the rate of a chemical reaction without being consumed. This is done by not adding in energy, but lowering the activation energy in the chart here for a chemical reaction to take place. Catalysts don't get used up in a reaction, which is why they're very efficient molecules, because they continue to get reused over and over and over again. So they're very, very efficient in terms of their use. When drawing a reaction energy diagram, such as what I have here, and what I want you to notice is that this is an exothermic process. Yes, the products are lower than that of the reactants. But notice what happens to the hump or the activation energy when a catalyst is added. It is simply lowered. Where the reactants start does not change, nor does where the products end in regards to the reaction. The only thing that changes as a part of this is the fact that the activation energy is lowered. A lower activation energy results in a significantly faster chemical reaction. So if I were to ask you to draw a reaction energy diagram and then ask you to redraw the diagram but within the presence of a catalyst, the only thing you're going to change is the size of this hump here. That's all you're going to change, is the size of the activation energy. Just make sure that it is lower than what it was previously and you're fine. Just don't change the reactants and don't change the product's energy. Only change the activation energy. All right, so just a quick little review in regards to things that impact rates of reaction, and you can take a look at that at your own leisure, but I think I've reviewed the previous content pretty well. Hopefully you're going to be in good shape on that. Let's move on to our next topic.